Oh, hi. I didn't see you there. We're going to talk about hypothesis tests in this video, also known as a significance test. Great. Oh, yeah. Different ideas. We're going to cover the hypothesis test itself and what the p-value is, the proportions test, the means test, power and error, and connection to confidence intervals. So first, the hypothesis test itself. So I talked about this before, a lot in class, but the hypothesis test is basically like someone saying, oh, I can make 80% of my free throws. And you're like, oh, bet. And then they take 10 shots and they only make 3 of them. And you're like, well, if you really make 8 out of 10, making 3 out of 10 seems pretty unlikely. And that's basically what the p-value is, right? The p-value is the probability that we observe a sample this extreme given that the null is true. That's basically what the p-value is. So you convert that into words, slap some context in it, you've interpreted the p-value. The formula for that standardized test statistic, it's statistic minus parameter over standard deviation. I'm sorry that this got all formatted weird, but basically z equals x minus mu over sigma. It's just the statistic is probably going to be x bar, parameter is mu, and the standard deviation is sigma over the square root of n, right? So there's formulas for this on the AP Stats formula sheet. That's for a z-score or a t-score. So z is for proportions, t is for means. Every inference thing ever is state, plan, do, conclude. You're going to state the hypotheses, make sure you define the parameter, plan your inference procedure by checking conditions and naming the test, do the calculations. The calculator is going to do the work for you. You just got to tell me the p-value and then either the z-score or the t-score, depending on what kind of test you're doing. Also degrees of freedom if you're doing mean. And then you conclude. So you're going to reject or fail to reject and then make a conclusion in context about the alternate. I said that really fast. Don't care. Proportions. The conditions for a hypothesis test for proportions. You need randomness, which is usually stated. Normality we get from the large counts. We're going to do np greater than 10 and 1 minus p greater than or equal to 10. And then we also got to do the 10% condition. The population size must be at least 10 times the sample size. So those are conditions for proportions. Conditions for means are basically the same thing. The only thing that's different is how we get normality. So for means, we either need the population to be normally distributed, we need the sample size to be at least 30, or a graph of the data doesn't look extraordinarily terrible. We need any one of those 3 things. We want the population being normal is the best way because it's super fast. If not, a big sample size will do. Man, I hope I don't make a graph, but maybe I have to. Minimum sample size is irrelevant. Deleting that because that was for confidence intervals. Power and error. Type 1 error. Remember, type 1. Reject when you shouldn't have. Thank you, Sally Bywater. That's when calculations led us to reject the null hypothesis when in reality the null was true. This occurs with a probability of alpha. The type 2 error is the calculations led us to fail to reject when in reality the null is false. That occurs with probability beta. Power is the probability we correctly reject the null hypothesis. That occurs with probability 1 minus beta. The way we increase power, because we like power, right? We want to correctly reject. Power increases with sample size and significance level. There's a connection to confidence interval when you do a two-sided test. So a two-sided hypothesis test, so that's when we have not equal in the alternate, that's logically equivalent to a confidence interval. So for example, alpha equals 0.05 is equivalent to a 95% confidence interval if this, very specifically, if this is in your alternate. If you have less than or greater than, it's not logically equivalent to a confidence interval. Perchlorate is a chemical used in rocket fuel. People who live near a former rocket testing site are concerned that perchlorate is present in unsafe amounts in their drinking water. Oh, hello, little whiff of hair. There, it's gone. Drinking water is considered safe when the average level of perchlorate is 24.5 parts per billion or less. So this or less is safe. They think it's not safe. So we're really going to be looking for greater than 24.5. I'll make sure I point that out. A random sample of 28 water sources in this area produces a mean perchlorate measure of 25.3 parts per billion. which of the following is an appropriate alternative hypothesis that addresses their concern? So I want to point out this is irrelevant for your hypothesis statements. Your hypothesis statements should be about the parameter. So they think it's unsafe, so it should be greater than 24.5. Has nothing to do with 25.3. So we're looking at D. Thumbs up. Yeah. An experimenter conducted a two-tailed hypothesis test on a set of data and obtained a p-value of 0.44. If the experimenter had conducted a one-tailed test on the same set of data, which of the following is true about the possible p-values that the experimenter could have obtained? I want a disclaimer. This question is weird, but it's fine. I'm going to show you anyway. Got a rough normal distribution. We got some area here, and we got some area here. We have area in both tails because it's a two-sided test, right? So since the p-value is 0.44, that means this is 0.22, and this is 0.22. Now they're saying, well, what if I had done a one-tailed test on the same data? Well, they didn't give me enough information to know if I'm looking at this one or if I'm looking at this one, right? I don't know which tail I'm looking at. Also, they didn't tell me, well, would I be looking at maybe this space instead? Right? So they haven't told me anything. All I know is that this is 0.22, and since I could go the other direction, this is 0.78. So the possible p-values are 0.22 and 0.78. I think it's a little odd of a question, but I did want to point it out. Suppose that on a hypothesis test for a single population mean, HA is where mu is less than 10, assume that the alternate is true. The mean is in fact less than 10. For a fixed sample size and significance level, the power of the test will be greatest if the actual mean is which of the following? Oh, dang. Well, we know power is increased with sample size and significance level, but they're not letting me adjust that. So basically now it's just what would be the easiest to detect this alternate hypothesis? Well, they're saying mu is less than 10, right? So I'm just going to pick the one that's furthest into that, right? 8 is the one that's the most less than 10. I think you understand what I mean. I would detect that difference the most easily because it's furthest into my alternate hypothesis. A large university provides housing for 10% of its graduate students to live on campus. The university's housing office thinks that the percentage of graduate students looking for housing on campus may be more than 10%. The housing office decides to survey a random sample of graduate students, and 62 of the 481 respondents say that they are looking for housing on campus. On the basis of the survey data, would you recommend that the housing officer consider increasing the amount of housing on campus available to graduate students? Give appropriate evidence to support your recommendation. Okay, appropriate evidence, or something like, do the data support? Is there enough evidence? Do the data provide convincing evidence? Words like that mean do a hypothesis test. So I need to do a full state plan to conclude. I should be able to get state and plan on this slide, and then I'll make a copy of it so I can do and conclude. So 1, got to state the null hypothesis. They think the percentage of graduate students looking is, they provide 10%, right? So HO is that P is equal to 0.10. The housing office thinks that it might be more than 10%. So HA is P is greater than 0.10. And I need to define the parameter. So where P is the proportion, true proportion, of graduate students looking for housing on campus. Okay, going to move on to my plan step. So I need to name the test. We're going to be doing a 1 proportion z test. We will conduct a 1 proportion z test. We have to check the conditions. Does it say the sample is random? Yes, it does. Since it's a large university, it's reasonable to assume there are at least 4,810 graduate students. At this university, right? So now I need to do large counts because this is a proportions example. So I'm going to do 481 times 0.1. So this is the proportion from the null hypothesis. That's 48.1, which is in fact greater than 10. And then I'm going to do 481 times 0.90, which is equal to some number, I'm sure. 432.9. Which is greater than 10. So since large counts is met, the sampling distribution is approximately normal. Okay, so that's my state and my plan. Now we're going to do and conclude on the next slide. Remember, do is done completely in your calculator. So this is where I pause you. He's back with a p-value and a z-score. Okay, so got my p-value and my z-score. That is a small p-value. So in my conclude, alpha equals 0.05, our standard alpha. We reject the null hypothesis. There is enough evidence to conclude more than 10% of grad students at this university are seeking on-campus housing. Now, all this is great, but I didn't actually answer the question they asked, right? Would you recommend they consider increasing the amount of housing? Yes. The office should increase housing. That last sentence isn't usually necessary for hypothesis test, but because of the way this question was worded, we did need to make that actual recommendation. I'm out of slides. Peace.